Okay, great. So can you guys, yeah, okay, good. So first, let's look at Gaussian elimination. So you guys have said like you know that, but before that, like we know there is a method of determinant to determine if a system of equation have a solution or not. So determinant is like this. So when we have a system of linear equations like this, so for here we have two variables and two equations. So actually for each of the equation, linear equation, it's like a line in the space. And for here, we want to find the intersection of those two lines, right? By solving this linear system. And the solution or the conclusion of this this determinant stuff is, do you guys know determinant? If you know, type of 1, otherwise a 2. Okay, good. Good. Okay, so so for this linear system, we can write it into a matrix equation. So basically, this is the matrix A and this is B, right? So we are trying to solve AX equals B. And usually B is like a column vector and A is some kind of matrix. For here, it's a 2 by 2, a square matrix. So because we want to use applied determinant, so A has to be a square matrix, right? For other cases, we can't apply this rule. So for the determinant, let's say A, B, C, D, A, B, D, C, then the determinant is AC minus BD. And if this determinant is 0, what does that mean? That means AC is equal to BD, right? And in that case, that usually means that those two lines are either in parallel or they are the same, actually, right? So in that case, it's the solution for the system is kind of tricky because they either don't have intersection or they have all the points in the line is the intersection. And for the other scenarios, if AC minus BD is not 0, then we can always find the only solution here, right? So that's actually the rule for the determinant. And the method of determinant actually applies for all these square matrix A. But so for this method, we can determine whether a system equation has a solution or not, but we don't know what's the solution, right? So we need this Newton's the Gaussian elimination to find the actual solution for the exact solution for this system. Okay, so let's look at this example here. So for this example, we have a 3 by 3 matrix A and a 3 by 1 B, right? So what is Gaussian elimination? The intuition is actually very straightforward. We try to eliminate the coefficient of those or the parameters here. We sometimes call it efficient or coefficient or parameters here. We try to make them 0, right? What's the benefit? The benefit is if we have something like this, right, we can directly get Z. So that's our goal, right? Because we want to know what's the actual value of X, Y, and Z. And if we can start from one thing and then we apply it back, something called back substitution, right? So if we know Z and then we apply to here, we know Y, and then we know X. So in this process, through this process, we can finally get the final answer. And this is the idea for Gaussian elimination. For example, for this example, for this case, so we first try to make this 2 to be 0, and also this minus 6 to be 0. So this is the first step. And for the second step, we actually try to make this 5 to be 0. So okay, let's look at the matrix format. So this is called the augmented matrix when we append the B to A here. So actually, this is the way we how we solve a linear equation. And as we talked about, the first step is we are trying to make those 2 and -6 to be 0. How do we do that? We multiply a factor on the first equation, because because if we multiply a non-zero factor onto an equation, it doesn't change the equation at all, right? So then we can add them to the second and third row to eliminate the first element or the first column elements in the matrix. Yeah, except for the first row, right? Because we cannot eliminate this one. After that, we do some simplification because it's simple, right? And then we try to do the same trick and apply the second row to eliminate this number, right? So for here, we apply -5. The factor is -5. If we multiply -5 and plus to the third row, then we can get something like this. And this is exactly what we want, right? If we can write the equations in this way, we can use back substitution, right? So clearly here z is 2. And then if we put z is equals 2 here, and then we can got y, and then we got x. So finally we got x like this, I guess. And this is the how the Gaussian elimination works. So far, any questions? Okay, cool. Another thing is Gaussian. Sorry, not Gaussian. Another thing we covered today is the nonlinear equations. So for nonlinear equations, we need to apply Newton's method. And okay, again, so since you guys have never seen Newton's method before, we can talk more details about this. So Newton's method is trying to solve the nonlinear systems or nonlinear equations. So in reality, we don't have so many linear equations actually, right? So think about the phenomenon, like the natural phenomenon. We don't have, it doesn't make sense if it's linear, right? But sometimes we simplify or approximate it by a linear system to get an intuition from it, but most of the time it's not linear. So in that case, we cannot directly apply Gaussian elimination to solve the problem, and we actually need something like Newton's method. And let's look at this example, because we will start from one dimension because it's straightforward and it's easier to visualize. So let's say we have a function like this, y equals fx, and obviously it's nonlinear, right? So we are trying to find the x that can meet the requirement of fx equals 0, which is here. And how do we do that? So Newton's method said here, the first thing is we begin with the initial guess, x0. So what's initial guess is we can think about it as like we randomly pick some point here. We can even point here, pick something here or here. It's the same. But the tricky part is the initial guess is very important, and Newton's method can converge very quickly with a good initial guess, and otherwise it might not converge at all. So this is tricky, right? Because this is kind of trying to find something, and right, it like in many of the problems like this, like optimization or like machine learning, you right. So nowadays machine learning is hot, and everyone is trying to use it to do some some prediction or classification, but the background math behind it is like some kind of numerical way to find a specific point which meets some requirement of, let's say, minimize, or let's say equals 0 or something. But the common thing is we always start from an initialization. But how do we choose that? Anyone wants to talk about how to choose the initialization point? Because here you said the initial guess is very important, but how do we make sure we get a good initial guess? You can directly unmute yourself if you wanna. Yeah, let's say for this example. Okay, maybe let me first cover more of the talk about the whole process of this Newton's method, and then come back to this initialization question. Okay, so how after we somehow get an initialization, let's say this is a good one. Okay, we somehow got a good initialization, and then we apply this. We draw the tangent line at this point, right? So this is a tangent line for this function. This is easy, right? If you get the derivatives, and then you can directly get this function. So for this line, because this is a linear line, and we have already learned how to solve a linear equation, right? It's Gaussian elimination. So we can use Gaussian elimination to find this point. This is the intersect of this linear line with this when y is equals to 0. And we say this is x1. As you can see, this is our target. Our target is R here. And this is our initial guess. As you can see, so after the first step, actually we get closer to our target, right? And that's basically the idea of Newton's method. And we can do this again and again. So let's do one more time. x1, we can also find so for fx1, it's obviously not 0, right? So we can find, so we can do the same trick and draw a tangent line here, and then find the intersection of this line to the y equals 0, which is x2 here, right? As you can see, x2 is closer to R compared with x1. And we do this again and again and again. After a lot of iterations, we will get something maybe very close to R, or even get R. So that's how the Newton's method works, right? And like there are several things important. The first thing is initial guess is very important. And also we have to draw this tangent line. And because we already know how to solve the Gaussian elimination, so we can directly find this x1, x2 every time we apply Newton's method, and hopefully we achieve something like usually we will have a tolerance. So tolerance is something we usually call it epsilon or something, which means that the distance between our current solution to our target is smaller than a certain threshold, and in that case we accept the solution. We think it's good enough, right? Because it makes totally sense, right? Because in reality our function is already a approximation of our system, so we don't actually need to be that concise, right? Because everything is have some errors. So if we make some small tolerance, then we can believe we already find the solution. So this is the basic idea for Newton's method. Okay, and then let's go back to this initialization question, right? So since, let's say for this example, how do you think, what is a good initialization? How do we pick a initialization? Okay, let me give you guys 2 minutes to think about this question. How to find a good initial point. Or do you think x0 is good or not? If you want to discuss, you can directly unmute yourself, or you can type something in the group chat. Okay, so I'll answer it. So actually, we don't know how to choose a good initialization. That's very unfortunate. But we have some rules to try to guess a better one. So the first thing is you can try multiple initialization, right? So even from the probability perspective, you should be able to get one if you try like a large number amount of trials. So basically that's kind of trial and error. Also, people do some random initialization, try to reduce the your personal bias, and also you can try you can try to learn the property of this nonlinear system and see, and if you draw something, actually for this one, you can, any guess is okay. But for some of the nonlinear system, if you like the comments here, if there is a function like this, right, then you cannot randomly choose any initial points. So in that case, you have to study the property of the function and try to make a better decision then. Okay, so this is Newton's method. After we introduce the theoretical parts of this Gaussian elimination, Newton's method. Oh, okay. Also, we have like Newton's method can also work in higher dimension. It's similar, but we can think about like, I mean, the idea is similar. It's just like to apply it to like 2-dimension or 3-dimension. Okay, so so this is, any questions so far? Okay, so let's move on to the coding part. So I hope you guys can try to understand this. I don't like expect you guys to totally understand every part of this and code them, but if you can know the more details about those methods, because in Matlab you have the solution or the functions built in to directly solve a linear function, a linear equation, but you will benefit a lot if you understand why. So let's move on to the coding part. Okay. Let me first stop share my Matlab. Okay, good. So this is my Matlab. Okay. Let me first create a script and call it week 4. So the first thing we want to do is we want to implement Gaussian elimination, right? So we want to define a function to implement this. So what's the input and output? The input is A. So we are trying to solve the matrix, the equation of AX equals to B by Gaussian elimination. And we also assume A is square, which means the number of variables equals to the number of equations here. So yes, so this is our problem, because we for a lot of almost actually a lot of linear equations we can use this Gaussian elimination, right? So that's why we want to write a function here. Okay, so I'll leave you guys like 10 minutes to think about how to solve this one, and I'll give you some hint. Okay, so first, since this is a square matrix, we assume A is square. So the first step is we get the dimension of this matrix, right? So let's say it's an n by n matrix. And then the second thing is, I think we need to, like we just covered in the material. It's like we have two steps. The first step is to eliminate the most of the coefficient to be 0, right? And let's say the first step is eliminate. Whatever. So, and the second step is like back substitution, right? Back substitution. And then you guys can first think about like how many for loops or while loops we need here. Do we need a nested for loop? Okay, so I'll give you guys like 10 minutes to think about this first. And still, if you wanna discuss, you can directly unmute yourself. Can you just make augmented matrix for the row reduction and do ref? So can you clarify more about, are you answering this question or for the general new Gaussian elimination? Oh yeah, for sure. Yeah, you can definitely make an augmented. Yeah, that's yeah, definitely you can do that. Okay, 5 more minutes. This is not so straightforward, but you can try to think of something like a pseudocode, like the structure, and how to have access to each element in the matrix of A and B. Okay, 1 more minute. Anyone wants to talk about your idea? Okay, let's do this together. Okay, so first let's do row reduction. So we definitely need for loops, right? And I think we need nested for loop in order to have access or index the matrix of A. So for row 1 equals 1, 2, n, right? And we also need a column. So the column is actually every time we only work on one column, which is the current row. And then for row 2, if we think about So here we have, actually we have 2 rows, right? Because when we do row reduction, we will apply a factor to one row and then add it to the other row. So this is a row, actually this is row plus 1, right? Because we don't need to do the current, apply to the current row. So, and then we need to calculate a factor, right? As we talked about in the material. So a factor is actually when we do a simple calculation, it should be minus a row 1 column divided by a row 2 column. Right, so this is our factor. And if you look at the factor, we are trying to do some division, right? So, but actually we cannot, we don't know whether this is 0 or not, right? So if it's already 0, then actually we don't need to do anything. But so we do this only when, if a row 2 column is not 0, okay, right? Okay, so now we have the factor. And after we have the factor, then we know a row a row 2, because we are trying to apply the first row to this, anyway, we are trying to reduce the row reduction, right? So it's a row 1 plus a, factor multiply a row 2. Yeah, so we have to apply all the, so this is the scalar and this is a vector, and when we do this multiplication, basically it's applying a multiplying factor to every element of this in this vector. After we have row, we also need to apply the same thing for B, right? Otherwise, it's not equal anymore. So, and since B is only 1 column, right? So we don't have to do this column here. So it's B row 1. It's the same with the previous line, just change A to B. Factor multiply B row 2. Okay, so this we end the for loop, and end. Okay, now we finish the row reduction here. Okay, so how about back substitution? So similarly, so like when we want to return something, we really need to initialize it, right? That's we talked about the example of summing some numbers, sum up some numbers. So right, like that, we also have to initialize like sum equals 0 first, right? So for here, it's the same. We need to initialize like x equals 0, sorry. Because we are trying to return n by 1 matrix, so we initialize it like this. And then also for row because here we are doing back substitution, that means we start from n and then go back, right? So we start from n, the n's 1, and then every time the step size is -1, and then we go back to 1. So here x row first is equals to, let's say, b row. Then for column equals 1 to, column also we need to go backwards. So it's from n to, and step size is -1, and go to row +1. Because we don't have to, for the other columns, it's already 0, so we don't have to do that anymore. So x row is x row minus x column. This is how we solve the each of the element, right? A row column. This is our for loop. And finally, we need to check how we, because x row is x row divided by a. That's it for oh sorry, so we have to end our function definition. This is our function, right? So if we do, let's say, if we do linear solver, we just do a 1 matrix, okay? 3, 9. Linear. Okay, yeah, here. So linear solve, yeah, sorry, linear solve, not linear solve. So here we get the right answer. So let's think about the ideas. Go through this function. So first we do this row reduction, and we have to calculate the factor. And one important thing is we have to make sure this is not 0. And then we go back, and this is called back substitution. So we have to start from the end to the front. Okay, so this is for the Gaussian elimination. We have 8 more minutes, and I'd like to give you a quick example about the Newton's method. Okay, let me first stop share and share this one. Share screen of this one. Okay, so here, can you guys see this clearly? If you can, please type a yes, or otherwise no. Okay, let me try to zoom a little bit. Okay. Let me see, how do I zoom it? Zoom. Can I zoom? Oh, here. Okay. Yeah, maybe you guys can first, let me go through the question first. So this question is talking about, okay, let's skip this background part. Actually, we are trying to solve this linear system, right? And we are trying to apply Newton's method, right? And we give you some conditions, like the tolerance we talked about. It's a 10 to the power of -3. And then initial gas. So here we give you an initial gas of this. And we also give you a maximum number of iterations here, right? So this is how we use the tolerance. So whenever we find this absolute of fx value is smaller than this tolerance, and we think it's already good enough. And so here we give you some hint, like if you use, we want you to use while loop. You must use a while loop to iterate the methods. And here, if your while loop does not converge within n iterations, so n here is 100, you must stop the loop. And also, we give you guys the formula to calculate the Jacobian matrix of the system here. Right, this is not our current homework. Yes. This is, I just put this as an example for you guys to look at. So this is our question. And of course, we give you a fancy background to make this happen, to make this nonlinear system reasonable, right? So So how do we solve that? Maybe you guys can first take a picture or a screenshot of this problem, and then I'll go to the solution part for this question. I'll leave you guys 1 more minute, so I'll start talking about solution at 10:47. Okay, so I'll stop share this question and I'll go directly to the solution part. So this is my solution to the question we have. And okay, so I'll first copy this into, oh, sorry. Okay, so I'll first copy this thing into the chat box, chat window. Oh, where's our chat? So this should be the actual solution for this question, specific question. So, so usually for Newton's method, we have 3 parts. One part is to, oh, I think I make some mistakes here. Let me see how I can undo. Okay, let me. Okay, so let me copy again. I think I did something wrong. Copy, and then. Okay, so this should be the correct answer. And let me share my screen and talk for how. Okay, so this is our solution for Newton's method. This is our main function, and this is the actual nonlinear systems we have, and this is how we calculate the Jacobian matrix. So usually we have those 3 parts. And let's look at the main function part. So we have a while loop here, and the input for this function is epsilon, this tolerance, and the initial gas, and the maximum iteration, right? So we have a while loop, and while our absolute is larger than this, we should continue. Otherwise, we should break, right? And if our iteration time already exceeds this n, which is 100, we break. So basically, this is the idea how we apply Newton's method, and this is our equations in the material, and this is how we compute Jacobian matrix. Okay, so I think that's it for today. I hope you guys enjoy the material, and see you next week.